Hey everybody, my name's Ariel Caplan, and I'd like to welcome you to my talk, The Trail to Scale Without Fail, Rails? Before we hop into the content of the talk, I want to just take a moment to step back, have a look at the image on your screen right now, and I want you to think about what's the reason that I chose this image, which doesn't really seem to be related to scale at all for this talk. So to me, what I see here is there's one user, one device, having one experience. And when we talk about scale, it's really easy to get lost in big numbers and all kinds of fun technical details. But ultimately, what we're really trying to do is to create this kind of individual experience many, 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 many times over. And I think that when we think about things that way, when we make sure that we're not focusing just on average response time or things like that, but we're really thinking through what's the ultimate user experience, we get to a much better result and we come to much better solutions. Now to jump to the other side of the spectrum, really to dive in and get technical. So what do you think is the biggest Rails app in the world? And I started thinking about this probably a few years back when I saw this talk at Ruby on Rails called The Recipe for the World's Largest Rails Monolith by Akira Matsuda. During that talk, he described CookPad and the traffic that they get. He talked about a number of other metrics in terms of just describing the gargantuan scale of their Rails monolith. But the one I want to focus on, kind of arbitrarily chosen, so sorry about that, is requests per second. And in this case, he said that they have 15,000 requests per second. Okay, but it was, a pretty impressive scale. At least I certainly thought so at the time. Working on my company at the time's app had maybe a few hundred requests per minute. So definitely a very different scale. The next year at RailsConf, Simon Eskildsen, hope I pronounced that right, gave a talk about Shopify, where he described that they have 20 to 40,000 steady requests per second, peaking at 80,000. I'm going to really focus on that 20 to 40,000 though. And actually just a few months ago, Shama, who is a VP of engineering at GitHub, said that the GitHub API deals with over a billion API calls daily. Now, I don't know if this includes Git pulls and Git pushes, and if this is really representative of their overall traffic. I'm going to assume that it's, yes, within the general order of magnitude, because that's about the best information that I can get. So we have a few different Rails applications really working at scale that we can use as kind of examples from the community. So if we want to compare them all, we normalize them to requests per day. So CookPad is about 1.3 billion with a B requests per day. Shopify is at 2.6 billion. Now that was in 2016. I don't know how CookPad's grown since then. I know they've opened in a few more countries. Shopify has nearly doubled the number of stores that they're hosting. So I guess that they're probably around 5 billion by now. GitHub, again, just a few months ago, was at 1 billion. And Cloudinary, where I work, looking at our entire system, we take about 15 billion requests per day. And I want to point out these are not just regular requests that you might think of being associated with the Rails app. These are actually, for the most part, media requests. So it's really, it's like take the other three and double them, and then that's basically the scale of Cloudinary. So just to give you a sense of where we stand in that world. Again, I've played with the numbers a bit, so I apologize. Now, when you think about a typical Rails app, right? So you have a client computer, makes a request to a server. The server probably talks to a database, gets some information back, and finally sends some kind of response back to the client computer, whether in HTML or JSON format. When we're dealing with Cloudinary, it's a little bit different. Now I'm going to, again, keep this very simplified view of the app, even though both your apps and our app are much more complicated in terms of their architecture. So Cloudinary generally is going to be serving not HTML or JSON, but images and videos. And in fact, it's not necessarily just the images and videos that we have stored. We are probably going to do some kind of transformation, make some derivation of the image. And if you've ever done image processing, you know that that's actually a very computationally intensive process. And that's what we're doing on basically each of these requests. So let's just dive a little bit deeper into what does Cloudinary actually do, because I do think that it's really important, especially if you're not familiar with Cloudinary, to understand the nature of the service, the kind of use cases that we have, therefore the kind of traffic that we have, therefore the kind of load that we have to deal with, and that will carry us through the rest of the talk. So we're going to focus on one image and how it journeys through the process. So the first thing, of course, you can upload an image to Cloudinary. We store in one of our cloud storage solutions. Generally, it would be Amazon S3, but it could be Google Cloud Storage in certain cases. We then apply some kind of transformations, and we deliver via CDN. So probably most of you can imagine what uploading and storing are. The latter two items on the list are probably a little bit more confusing, and so we're going to go through them right now, just so you can get a sense of what's actually happening there. Since maybe you don't really know what transformations are, maybe you've never heard of a CDN, what even is that? So let's go through that. So imagine that you have an image. This is an image uploaded by a user. It's not really cropped perfectly, got a lot of open space there, and you want to fit it into one of a number of different layouts on your site. So you probably have to have a few different crops. There's the portrait crop and the landscape crop, and you want to crop also intelligently. You don't want to just kind of randomly take a slice or scale it in some kind of gross way. You really want to think about how you're going to crop it to the most interesting parts of the image. Maybe if you know that these are going to be avatars, you might want to really focus right in on that face. And the truth is, you might want to have different sizes and shapes of the image. Maybe you want to have a round form, maybe a nice big one for the author's profile page, but then when someone posts a comment, they have like a little tiny avatar. So many different versions of the same image. And the truth is, you might not want to stop there. So maybe you have this lovely arbitrarily chosen image, now cropped nicely for your layout, and you want to make it pop a little bit. So first we're going to enhance the colors a little bit. So watch closely as we do that, make the colors pop a little bit more, and then we say, what? Well, privacy is really important these days. People care a lot about it. We're just going to pixelate the face, help our users preserve their privacy. And on the top right, of course, we want to add our company watermark at about 50% opacity. So all these things you can do in Cloudinary by just adding on little bits to the URL. So we can see here on the top line, we have this improve indoor effect all the way on the right, which is what was doing the color change. We have a number of parameters: a width, a height, a crop mode, gravity, which we're focusing on the face. Q auto is another thing that we do, by the way. Again, I'm not trying to sell you Cloudinary. If it happens to, that would be great. But really, my goal here is that you really understand how heavy each request is. So Q auto basically takes the image that's going to be ultimately generated and tries to figure out what's the optimal compression, right? So are we going to compress it a lot? Are we going to compress it a little bit based on what's going to reduce the file size but keep the image quality very high for what's ultimately provided to the user for their visual experience. Then there's the pixelate faces, which identifies what's a face and then pixelates it. And then on the last line, we have the logo that we put on the top right with an opacity. You can see at the end of that long string, of course, the various crops and positioning and all that. And literally, you can go to this URL, and if you change any of the parameters, we'll generate a different image, starting from that initial image and then going down the line. So every request to Cloudinary, just to give you a sense of these 15 billion requests, right? It can be doing a ton of work when you think about the original image and how much we had to go through just to get here. Now, there's more, because actually your users are probably accessing your site from many different devices, different browsers, and it turns out that different devices and browsers support different image formats. So WebP is a really good example. It was supported in Chrome for a number of years. Firefox only gained support in late 2019. You have JPEG XR, which is kind of a Microsoft mostly uses that format. So you might want to serve it for Edge or Internet Explorer, but maybe not for Chrome. There's a JPEG XL, which is coming down the pipe, a little bit competing with AVIF. Cloudinary is a little bit closer to JPEG XL, just because one of the people in Cloudinary is a researcher who's been working on that. There's a lot of different, a lot of different formats basically you might want to serve, and you have to decide how you're going to send it. And so Cloudinary will generate the right image format based on the parameters of the request. finally, let's talk about CDNs. So here's the idea. You have your servers, maybe let's just arbitrarily choose Northern Virginia, US East 1. It's a very popular AWS region, but your users might be anywhere around the world, right? And when you make a media request, it can be very heavy. It's a lot of bandwidth, and you want to serve it from a server that's closer to them. But your app servers are only in one place. So what a CDN does is it provides you with a network of computers all around the world. And there are a number, by the way, of CDN providers, and they're growing all the time. But it's this network of computers around the world. CDN, again, is short for Content Delivery Network. So it's a network that delivers your content. And it will cache the media, right, the image or the video, very, very close to where the user is. And then, every time that a user from that area will request it, they'll get directed to whichever is the edge node, they're called, the computer on the network that's closest to them, and they'll be able to get the media from there. So it actually saves a lot of time in terms of how long it takes for the user to download the content. So now you're a little bit more familiar with how things work, the images journey through Cloudinary, and you can get a sense of what kind of traffic we're dealing with. And again, ultimately, we are serving things through a CDN, which you'll see is really important in a minute. A few other things that we do, though, because a certain percentage of requests do come from other things. We have Media Library, which is a GUI for media cataloging and editing. We have various developer APIs. We have some bulk operations, some available through the UI, some through the API. And those can be, by the way, really, really heavy, right? Bulk operations could be things like delete 40,000 assets. So, the bulk operations can be very, very expensive per operation, but I'm still not going to focus on them because that's all in all 0.3% of the total request. The more interesting question is, how do we serve the 99.7% of requests, which are the delivery pipeline? Delivery meaning transforming and serving media. And I'm just going to say, as a PS, we also do video. I will not focus on video in this talk. It brings in a whole different set of considerations and really difficult problems to solve. So I'm just going to focus on the simpler to understand case, which is the images. Now, before we dive into how Cloudinary solves problems at scale, just a word about myself, because I haven't introduced myself yet. So hi, everyone, again. I'm Ariel Caplan. I've been working in Rails since graduating the Flatiron School in 2015. I've been working at Cloudinary since 2018. I am at AM Caplan everywhere on the internet that matters, which is basically Twitter and GitHub. And by the way, if you are not in the conference and you do want to contact me, you're watching this video later and you want to get in touch, so please reach out on Twitter. My DMs are open. I'd be happy to answer questions that way. Last thing is, I really love conferences. I've been at a lot of RailsConfs and RubyConfs. I really love speaking, and I really love interacting with people and hearing your different stories and perspectives. And I say that and emphasize that just to say that there's a lot of really cool stuff coming up right now. I did not personally build just about any of it, and I'm really fortunate to have had the opportunity to talk to people who did implement a lot of this stuff. So I apologize if there are questions that I can't answer. I will be able to get the right answers from the right people. But my main interest here really is saying there's this really cool system, and the Rails world really needs to hear about these success stories of Rails at scale. And I just wanted to share that with all of you and to hear about your stories too. So let's dive in now to how Cloudinary scales. And actually, one thing I'm not going to talk about, by the way, is the scaling piece of it, meaning auto scaling. In other words, all of our servers basically are in the cloud. We can scale different groups up and down. There's a whole art and science to scaling and how to do it right. I'm not going to talk about that today, but just know that every service that I'm going to present to you today is something that can be independently scaled as you would expect, and we do. So the topics I am going to cover are: number one, dividing our service into various layers; number two, sharding; number three, the element of location, like geographical location; number four is deduplicating work, making sure not to do the same thing twice; not scaling, or deciding what to do when we can't scale just yet; and And then human factors, because those are no less important than anything else, and they do play a big role in our scaling strategy. So let's dive right into the first topic, which is layers. And anytime I hear the word layers, I just think of this quote from Shrek, and I'm sorry I can't do the accent, but Donkey's trying to say, oh, ogres are like layers, they like a layer cake, and Shrek gets very upset, and he says, layers, onions have layers, ogres have layers, onions have layers. You get it? We both have layers. And Cloudinary, like ogres and like onions, also has layers. So let's go through the basics of an actual request lifecycle in Cloudinary system. So this is going to be the more in-depth diagram compared with what we saw before. It is still not the full picture. There are a few things that we'll add, and there are a few things that we won't add, but this is really a more complete story. So we start at a user's computer. They're going to make a request, and actually it's going to hit the CDN first. The CDN will, if it has the asset already cached, it's just going to serve it back to the user and we're done. But if not, it's going to go further down the pipe. It's going to hit Cloudinary servers, and now we really start to do the work. So the first thing it'll hit is a system we call Seget. I put up a shield there because it kind of serves to shield our main app from the bulk of the traffic. Seget is a very simple service. It's written as S3 get here because that's why it's named that. It really just basically says, okay, based on the request URL and whatever other information we have, let's talk to the correct cloud storage bucket, which again can be S3, it can be Google Cloud Storage. It was named in the time when S3 was the only kind of storage. So there's your explanation of the name. So talk to the cloud storage, see if we have the information available. And if we do, then we can just send it back down the pipe and never bother anything deeper. In case we haven't created this asset yet, we will then talk to what we call the IO layer. And the IO layer, we call it that just because it's IO bound. And that's kind of the main app that interfaces with just about everything in the outside world. The IO app has access to our database, unlike Seget, which really can just talk to cloud storage. So it can talk to the database, it can talk to the cloud storage, and if it needs to do some kind of transformation, it will then talk to the CPU layer. The CPU layer is the more computationally intensive layer. That's why we call it CPU, because it is mainly CPU bound. Okay, so and of course, when the CPU has the resulting image, it will send it back to IO, back to Seget, back to CDN, and finally to the user's computer. So here's now the explanation of how the layers really help us. There are about 15 billion requests from the user's computer to the CDN layer. In 14 out of 15 cases, the CDN actually already has the asset stored, and so it never needs to talk to a Cloudinary server per se. In 1 billion of those cases, it will hit Seget. Seget will then pass on only about 15% of those requests. 85% of the requests it will deal with, but 150 million requests a day are going to hit the IO layer. And about 125 million end up, that's about the amount of times that we're going to call it a CPU. Now in terms of technologies, so IO and CPU are both Rails. They're actually the same code, but running on different servers for reasons we'll see in a bit. But Seget is in Go. So basically, we have the CDN to handle most of the traffic. Out of what's left, we have a little tiny Go app that handles most of that traffic. And then Rails is dealing with 150 million requests a day. So about 1% of the number I said earlier. So my apologies to the other companies that were on the slide. We are not technically that much bigger than them if you just look at Rails. But yes, if you do look at how much traffic our app is ultimately serving, how many requests our Rails app is the source of truth for, it is 15 billion. So that's how I personally justify that number. All right, let's talk about the CDN. And the truth is we clearly need it, right? If you're going to be a company that's involved in serving media, you need to be working with some kind of a CDN. But there are companies that have chosen to build their own CDN. There are companies who choose to buy, and we have gone the route of buying. We are paying different CDN partners, mainly Akamai and Fastly, to be able to handle that traffic for us. And so the big benefit is that 95% of our traffic isn't our problem. Now, to be clear, this is not the heaviest part of our traffic, right? There's no processing that needs to be done for all this traffic, but there are certain challenges that come with that kind of scale, and we just don't have to deal with them. So that's great. We can also leverage best-in-class service and features that our CDN partners give us that we didn't have to build ourselves, which is really nice. On top of that, there's a real benefit for reliability because we have this multi-CDN feature where we can basically switch between which CDN we're using to serve requests. And that means that if one CDN partner, for whatever reason, is having downtime, which is an extremely rare event, I can't think of a time that it's happened, honestly, in my recent memory, but theoretically, we could fail over to the other CDN. So there's a lot of benefits here of buying. Okay, and these are things that, to some degree, can carry over to any situation where you're thinking about build versus buy in terms of your own apps. The downside is we need to play by their rules. When you're paying for a service, right? The service has certain rules that you need to work with. So we have this feature called fauto, where rather than you having to decide in the URL what kind of let's say image it's going to be, you just write fauto, and then we'll say, well, given a certain browser and certain version, whatever it is, right? We're going to serve a JPEG 2000, but a different request, we're going to serve a different format. Maybe we're going to serve a regular JPEG. Maybe we're going to serve a different compressed format like WebP. So we can't handle that on Cloudinary's servers, right? We have to handle this on the level of the CDN because we don't want the CDN to have to talk to us every single time. So we have, this is just one example, we actually have tons and tons of custom rules that we have to write that's going to live on the CDN, and we have to do it in the language that they give us. And actually different CDNs have different languages, so we're maintaining a lot of the same logic in different languages. Also, every provider has their own invalidation system. So when someone, let's say, deletes an asset inside of Cloudinary, we then have to go ahead and invalidate it at the level of the CDN. Otherwise, the CDN will basically keep responding with that image until the cache expires. So we have to actually go in and validate that cache. Each CDN provider has their own invalidation system that we need to go ahead and work with, and batch requests properly and obey their rate limits. And it's actually a non-trivial thing. And I work on the billing team, so I'm very familiar with this part. We need to parse our log files to bill our customers. We can't just like look in our ELK stack to check our logs and say, hey, how much bandwidth did this customer use? We actually have to look at the log files from the CDNs in whatever format they're able to give us, and then figure out which customer requested a particular image, or a user requested an image belonging to which customer, because it doesn't hit our servers, so we need to then do it that way. So certain challenges, on the whole, still very, very much a good thing that we are not building it, in my opinion. We pay for great systems that do a great job. Segit. So Segit is a high throughput, very simple service written in Go. It's, I think, just a couple hundred lines of code. It's really not much. It's able to handle 85% of the requests that it receives. And compared with IO, which is, again, a Rails app, it takes up about 10% of the computing resources. So if you think about, bang for your buck, how many requests you can respond to for the amount of computing power, right? It's like 2 orders of magnitude better than our Rails app. So it's super fast, which is great, and really with very, very little code. And it's a really good way of handling a lot of traffic rather than having to have massively more servers to deal with. Instead, we can just have this very, very lightweight system that's going to handle most of the traffic and let Rails focus on what's more interesting. The only downside really is that we need to duplicate some Ruby logic in Go, and when the Ruby logic changes, we have to change the Go logic, or vice versa. There are times when we assume that, let's say, standard libraries in 2 languages work more or less the same, and they didn't. So little kind of edge casey bugs to fix. But on the whole, it's been a really great system that's helped us scale without scaling too much or too quickly in terms of our hardware to make it not worth it anymore. There are some other advantages of layers just in general. Layers can scale independently. So again, I'm not really diving that deep into auto scaling, but if you think about the ability to expand or contract any layer without other layers, like that's really great. So just to give kind of a very simple use case, let's say there are tons and tons and tons of requests for the same asset, Well, that's a CDN's problem to scale, but we don't ever even have to think about it because the CDN is handling that, that huge burst in traffic. So the CDN can scale without anything inside of Cloudinary really scaling at the same time, and that's true at any layer, right? Maybe there are a lot of very lightweight requests that don't require a lot of processing, so IO could scale and CPU would stay the same, things like that. And actually, we also slice things, right? This is really true for any kind of slicing. So if you slice horizontally as well, we actually have separate image and video clusters. That's another thing, right? Anytime you can kind of slice up your traffic, it makes it a lot easier to scale in a way that's very, very cost effective. And the other element is security. So actually, the CPU layer is very, very boxed in. It basically gets what you give it and does some computation and spits it out. But it can't talk to the open internet. It cannot talk to the database. The CPU layer is running a lot of different tools, a lot of open source tools actually, in terms of image processing. And it's not able to access the internet or the database because it has a very large, attack surface, right? Any of those open source libraries that, maybe there's some vulnerability, there's an opportunity to take advantage of that. And so we make sure to really lock down the CPU layer because it's doing a whole lot more. Whereas the IO layer, right, because it's separated, right, we can be a little bit more free and open with that because it doesn't have as many dangerous dependencies. So that's that in terms of layers. Let's move on to sharding, which I'm sure that many of you Rails 6 enthusiasts are looking forward to. And I want to temper your enthusiasm a bit with this lovely quote from Terry Tempest Williams: "Shards of glass can cut and wound or magnify a vision." And I think this is very, very true about sharding a database, that sharding a database both cuts and wounds. It makes life very, very difficult in certain ways, but it's also necessary in order to magnify the vision of your application to enable it to scale. So before I go too deep into how we shard, let's just talk about what even is sharding, because probably some of you have heard of it, but never really dove too deep into it. So sharding is actually a subset of the general concept of partitioning. The more basic kind of partitioning is vertical partitioning, which is generally not called sharding. The idea of vertical partitioning is that each database contains different tables. So you have one database on the left with the red and blue, with the red and these dark blue table, and then we have the database on the right with the light blue and the yellow tables. If you don't perceive colors, so that's fine. Just trust me that these are different colors, and the idea of vertically partitioning is to increase the ability to simultaneously read and write. So your tables are the same size wherever they are, but there's less load on each individual database. This was already supported in Rails 6.0. Then there's horizontal partitioning, which is also called sharding. And this is a whole different level of complicated. So the idea is that you have one table which is distributed across multiple databases. Okay? So we can see that each of these databases is containing the same information, or the same tables rather, but different rows within those tables. And the goal of horizontal partitioning is to keep the table size under control. So essentially, imagine if you have a table that's really, really, really incredibly long, who knows how many billions of rows. It can get very, very hard, even if your indices are properly set up. It's still very, very hard because your indices get so big that it takes time to search your indices. It's a really big problem, and so the solution is basically to split it across multiple databases. The challenge is that then you have to think about all these situations of how do you join against a table that's on multiple databases? That's actually a really hard problem. And how do you, by the way, decide which record goes into which database, right? These are all big questions that happen when you shard. So this is supported in Rails 6.1, but let's talk about how we do it in Cloudinary and how we solve some of these challenges. So we have one main shard for app-wide data, right? This is again in the general theme of vertical partitioning, so certain tables only live on that main shard. And then basically when you sign up for Cloudinary, you get what's called a cloud. It's kind of your own independent workspace. You can have potentially multiple clouds, especially if you're a higher paying customer. And basically the cloud is kind of, it's sort of its own independent entity. It's its own world, right? You can have different assets with the same name as long as they live on multiple different clouds. And that's fine. Okay, now in terms of how we implement this, so every cloud lives on one of several shards, and that cloud is 100% on those other shards. Okay, so like if it's a cloud, if it's a shard 1 cloud, then everything about that cloud is on shard 1. If it's a shard 3 cloud, everything about that cloud is on shard 3. All right, so essentially, once you know which cloud it is, right, a request comes into the server, we'll talk to the primary database. The database will say, okay, this request we're going to serve from shard 3, and then the entire request from beginning to end, we can work with shard 3 exclusively. So that's actually really nice. That's a pretty simple way to solve the problem of how do you split the table data between the different shards. The answer is it's really just per cloud. We've never had a problem where a cloud got so big that it needed to be split across multiple shards. That will probably be the follow-up talk maybe a couple of years down the road. So in terms of what it looks like in terms of our code, so we have this on-shard helper where you basically find the cloud from the request params, you call cloud.onshard, and then you get a block where you're doing your work against the shard that's been specified. Okay, now realistically, right, the code actually includes thousands of shard references. It's littered across everywhere, and this was not like, it's not an exaggeration. This is like I grepped and a word count, and it's thousands of references. And by the way, you also have to chart your test environment. Otherwise, you might not have your tests and production really be matching up. So it is not trivial to work with shards. Definitely not trivial at all. And the pro is that, look, fast is good at a certain point. If you want your app to have any sort of reasonable performance, sharding is not optional. It's not just like a nice thing. It's absolutely necessary. And the other really major advantage is flexibility. So we have the ability to say, for example, there's a customer who's having big spikes in traffic. Maybe let's put them on their own shard for a while, or put them on a shard with a few other noisy customers. So noisy meaning, just to be clear, right? Noisy is not a denigrating term. Right? It just means that they have like big spikes up and down in traffic. So at least hopefully they will not overlap with each other, or if they do, they're not hurting anyone else as much. The big downside is it's error prone. So take a look at this sample bit of code. We, again, find cloud from request params. We're just going to have this assets local variable available. On the shard, we're going to assign those assets. So it's cloud.assets.where tag is duck. So any asset where we have this duck tag associated with it. And then we're going to render that list of assets. So think of like an API call, right? This is not a delivery call. Now you'll note that where returns an active record relation. And then when we call render JSON assets on the last line, we're actually going to convert it to an array there by querying. And so the query happens outside of the shard block. And so it'll happen against, it'll try to do against a primary database, or it's not going to work at all. There's a lot of situations basically where active record is really helpful. It makes these these chainable relations, but it doesn't actually evaluate them. And so we need to be aware of that when we're working with shards to make sure that the actual evaluation happens when you're on the correct shard. Now the fix is pretty simple. You just add a 2A to that assets equals line. We want it to load eagerly rather than waiting to leave the on shard block, but it is something that happens. Now you might think, okay, but I'm sure this is fixed in Rails 6.1, right? Well, have I got some news for you? So kind of it's fixed. Here you have an active record base connected to, and you specify the role and the shard that you're speaking to, and then you call person.all. Remember that all is a relation. What's going to happen is that when you call people, afterwards, right? It's already been preloaded. So as soon as you exit the on-shard, the connected to block, it's going to preload that relation. However, it's actually not that hard to break the Rails 6.1 implementation because it only evaluates whatever is the return value of the block. And so here we are assigning this people local variable to just to nil above, doesn't really matter. Inside of the connected to block, we're going to call people equals person.all. Then we're going to do something else. And people is not going to be the return value. It turns out that we're going to try to load people from the default shard. So, active record in Rails 6.1 with sharding support does try to solve it for you, but it can't cover every case. And I guarantee you, absolutely guarantee you, if you do shard, you will have this problem sometime, earlier or later. I don't know. It will absolutely happen, and it's going to be a fun event to debug it. Write good tests. That's all I can say. if you're doing shards. But really, like, don't shard just because. Shard when you really need to, and try to push limits of your database before you hit there, because it is a very error-prone thing, and it's really hard to do it right. Location, or as every real estate agent ever says, location, location, location. So let's talk about regions at Cloudinary, how we put servers closer to the people that they are serving. At Cloudinary, we have 3 regions. So there's a default region in the US, which is what you get if you sign up for a Cloudinary account. But we also have the European and Asia Pacific regions for those customers for whom that's relevant. Generally, it will be a premium customer who really wants their service to be happening as close as possible to their users who are in the European or Asia Pacific regions. We have dedicated shards per region, so that solves most of the problem, right? So you have dedicated servers running the app, dedicated shards, and that solves most of the issue. But then there's a question about what about the primary database, right? Because the primary database, the apps need to talk to figure out what shard to talk to. So we have a few options for how we could have dealt with this, right? One option is run 3 completely independent systems. That would be very painful, and we didn't want to do that. Another option is that the other regions will just be slower because you have to really talk from pretty far away to hit the database right from Europe to the US region. We do not want that either. That would not be great. Another option would be to have some kind of multi-primary database where you have a primary in US, primary in EU, primary in Asia Pacific, and that they would basically update each other all the time. That itself would have been a certain degree of an ops challenge, but more importantly, when the regions were being set up initially, I think we kind of looked at the technologies that were available and decided it was just not a good fit for our needs. And so what we did in the end was we created our own system, which we call NRT Cache. NRT is short for near real time, because it's not exactly real time, but it's close enough. So here's how it works. In our US region, we have, as you saw before, our server and our database. And actually, there's a Redis instance that stands in the middle for some of our frequently accessed models. And so when you want to get some information, first you check, does the Redis instance have it? If yes, great, we can move on. If not, we're going to then talk to the database and check for that model. In this case, let's say it was a cloud, and then we'll cache it in Redis. Okay. Then we have, let's say, just take an example, the European region. It could be Asia Pacific as well, doesn't really matter. So again, server Redis, and we can talk to our Redis instance, but there's no primary database that we can talk to. And so instead, it will talk to a server in the US, get the information it needs, and then cache it in Redis. Now, when things have to be updated, let's say we updated some information about a cloud inside of the database. So we have a separate thing called syncer, which basically its job is to speak to the primary region, right, the US, to one of the servers there, get the information about what's been updated since the last time we checked for updates, and then put that into Redis. And generally that happens within 10 seconds of any kind of update, so it's pretty quick. In the US region, it's a little bit easier because everything is happening in the same area. So, okay, seems like a pretty straightforward system. Like, what could possibly go wrong? So, on August 4th, 2019, we had a little bit of a situation, kind of across the board. A big increase in error rate. Now, to be clear, a big increase doesn't actually mean that like all the requests were failing. We define a high error rate as, I don't know, something like 600 errors in 5 minutes. It's not actually very high necessarily, but it was a significant increase, and so we had a status report. Here's what happened. So there was just a regular deploy. Everything seemed fine, and out of nowhere, the error rate spiked. And for about 15 minutes, we had this high, again, comparatively speaking, error rate. And the cause was a problematic migration. So inside of the migration, we had something like this. We had something that iterated over each of the clouds, updated some flags, and then saved. And when you hit save, you update the timestamp on the cloud, which meant that syncer then would identify this as a model to update. And for all of our very high number of clouds, it was a huge amount of information to carry over to the other regions. happening basically per server there, and it just kind of gumming up the works that everything was incredibly delayed. And there was nothing we could do, right? Usually you have a problem, you increase the number of servers, no problem. More servers would just mean more problem. So what do we do, long-term to stop this from happening? The first thing is every time there's a code change, we check, is it going to update clouds in some large number? And if so, we need to find another way of accomplishing this goal. It doesn't come up very often, but it is part of our code review process now as kind of the immediate solution. But in the long term, what we actually did was we've been migrating to a new and improved system that does not have the same risk. All right, so location. Pro is that multi-region is really great for our customers and for their users. It gets a much faster service. The downside is it is hard to do right. It's hard to split your system in a way that's both safe and reliable and also fast. Okay, let's move on to deduplicating work. And I love this quote from F. Scott Fitzgerald. There are all kinds of love in this world, but never the same love twice. And with Cloudinary systems, we have a lot of love for our assets, our images and our videos, but we never want to love them the same way twice. We never want to do the same transformation more than one time. Why might that happen? So here's a challenge. Okay, we have the Ubi Shoes online store. They're releasing their R model, and it's like the biggest release of shoes in the last decade. So like tons of users are really excited about this, and they want to see the site. They want to get the information, but there's a block up, right? Basically, there's like a flag saying no, this site is not open to the public yet. And then the time hits, midnight UTC, whatever it is. They drop the block. Tons of requests come pouring in, and of course that includes requests for seeing the pictures of the shoe, and all that traffic gets passed on to Cloudinary. So huge numbers of requests for the exact same URL at the same time. That's really the case that we need to deal with. And so we have a system for locking. And the goals are as follows. Number one, we never want to repeat a transformation. Okay, ideally. But more importantly, we never want to block a job. And so we'd rather do something twice versus not at all. That's kind of the priority. But again, as much as we can, never to repeat something. And so the implementation of this is what I like to call a best effort locking system, where like we try to not do something twice, but if we really have to make a trade-off, so we will prefer to do something twice versus no times at all. All right, the system we use for this is something we built internally called Lopter. Lopter is a character in Norse mythology. You may know him by his more common name of Loki. And Loki sounds like lock. I didn't make up these names. Please don't blame me, but that's what the system is called, the locking system. So it sits right here. Basically it's talked to by the IO layer, and it is written in Scala. The way that it works is something like this. So basically when you want to work on an asset, first you request a read lock, which means don't write anything to this asset while the lock is held. Don't mess with it. I need it to stay constant. And then we create a record for the derivation of the asset, right? The transformed version. And we have to acquire a write lock before we actually go ahead and generate the transformation. And so what a write lock means is whatever process holds the write lock is allowed to write, but it's exclusive, right? No one else can do this at the same time. And what this means is that multiple processes can read the same asset at the same time, but only one can generate a transformation at a time. Now, this depends on the well-behaved client. Nothing is actually locked in any formal sense. What it really means is just that there's sort of an understanding between the different IO processes that if I hold the lock, you can't touch it. If you hold the lock, I will not touch it. Okay, so it's all the implementation of respecting the lock is entirely on the client. Okay, for speed, we use an in-memory lock table. We write in Scala, high concurrency, really fast, and it works great. It's a pretty simple system. Nothing too complex there. There are some concerns that it brings up. First of all, failure to release. What if one process starts working on a transformation and then, it just maybe the server just gets unplugged? I don't know. The lock never gets released, right? So we always want do it twice rather than no times. That's the general principle. And so we have a timeout on the locks. So essentially, if you've been working more than X number of seconds, then the next process in line will get a chance. And so we might, if it's a very long running transformation, we might basically have it done a few times, and then one of those will eventually return one after another after another after another, and then at some point we're not going to do it more than that number of times, right? Once the first process finished, so then whichever is the next one to ask for a lock is going to be like, oh wait, no, actually the transformation finished, so I don't actually have to do the transformation anymore. Another concern is downtime. What if your locking system just kind of is down for a minute? So the answer is sort of funny. We pretend every lock request succeeded. Again, following the principle of better to do it twice than no times at all. This would not work for something you need for data consistency, for example, but it works great for something that you really just need for performance and mostly trying to deduplicate work. How do you scale your locking system? So we have a cluster where each request, and again, this is about a good, very intelligent client. And well behaved. So the client hashes the information basically. Here's the asset I'm requesting. It creates a consistent hash, and that will decide which server it's going to talk to within that locking cluster. So a lot of the logic is on the client, which keeps the locker itself pretty lightweight. The big pro is resiliency to traffic surges, like the one I described for the RUB shoes or Ruby shoes, however you want to pronounce it. It's really great, and that's a use case that we have all the time, right? A news article just opened up. I mean, there's lots of things which go on the internet, and like immediately there's tons of traffic asking for that specific thing. The downside is that if there are too many processes in line for a lock and they don't get released fast enough, then there can be timeouts. It doesn't happen that frequently though, so honestly it's not a really big con. More importantly, it's not 100% reliable, right? It's not on the level of data consistency. It's a good enough system. It's definitely not perfect, but that's not the goal, right? Because again, we prefer to do the same work twice rather than not at all. All right, not scaling. To me, this is actually like the coolest part. So I'm really excited. There's a lovely quote from Tim Ferriss: "What you don't do determines what you can do." And in this case, we're going to talk about when we choose to not do something that we've been asked to do, or at least we don't do it right away. Okay, the general principle is we always want to limit the impact of an individual customer on the entire system. Because, would you rather deal with one dissatisfied customer or thousands of dissatisfied customers? Because, a customer spikes their usage. It takes a certain amount of time to respond to it, to scale up your computing resources. It's much easier to talk to one dissatisfied customer, to explain the situation, to help them correct the problem, tell them figure out how not to spike in that way, to say, hey, can you wait 5 minutes and then we'll deal with this spike. Most of the time, like, our system is able to handle, spikes, right? We have enough capability there, but we recognize there are times when someone is going to have a certain spike in some kind of usage that is going to cause a problem. So we need to be able to create a situation where maybe a few customers here and there will have bigger incidents of downtime or increased latency, but it's not going to impact everybody. That's the fundamental idea. So how do we do this? Well, there's rate limits in a very explicit way in terms of our APIs, and then there are sort of these quiet rate limits, where we do throttle individual customers if they hit a certain amount of scale. And in general, we're trying to do two things, right? We're trying to manage scarcity while eliminating scarcity. So eliminating scarcity means scaling up our computing resources, but because it takes a certain amount of time to do that, even if you have it perfectly fine-tuned and automatic, AWS is a minimum of like 1 minute to begin to respond to any kind of scaling event. That's like their minimum latency to auto scale, just as an example. So we have to manage scarce resources when there's a lot of demand for them. And so we use a fair queuing system basically to do that. And of course, we also like to do background jobs. Background jobs help us to spread out the impact of a spike event. All right, rate limits. Heavy API calls have a strict limit. And then for, again, there's sort of like internal thing where we have locking that that is, it's not like exactly a rate limit per se, but there are calls that are not strictly rate limited, but at a certain point you will hit this throttling from locking. That's usually when we get a call to customer success, and then we can handle that through the appropriate channels. Again, it doesn't come up for most of our customers at the scale that they're dealing with. Now, in terms of the fair queuing system. So the idea is basically every job is assigned a number of slots, and we have a queue of queues mechanism to allot the slots to clouds. Now that's a lot of words, and it's very vague, so I want to do this graphically. So imagine that we have a bunch of requests that came in from different customers, so each one of these, basically there's a color and a glyph, and there's no significance to which glyph it is. It's just a way of making sure that even colorblind people watching the talk are going to be able to understand what's going on here. But don't ascribe too much importance to which glyph I chose for each color. It's all good. So a bunch of requests that came in, and we could just basically handle them in the order that they came in. That's one way that would work. But it can give an unfair advantage to a customer that's having a big spike. Instead, what we do is we create a queue of queues. So each customer gets their own queue. We put all those queues in one big queue, and then we can start processing them in a fair way. So we start at the top, right? We process the first customer's job, go ahead to the next one, process their job, next one, process their job, right? And you can kind of imagine how this goes. Go back to the top, right? You get one more job. Okay, nothing for the red, but the yellow has one. Go back to the top and just go kind of all the way down the line till we're done. And I want to kind of take a step a little bit more, really understanding the complexity here, because it's not like there's only one job being processed at a time, right? We work with multi-core machines. So imagine, again, taking a very simple way of looking at it, imagine that it's a 4-core machine, and each core can process one job at a time. So maybe the first 4 items in the queue, again, the queue is the queuing system is deciding what's the order, but then each core is going to basically process whatever is the next job in the queue as you go until we're done. We've eaten up the whole queue. Okay, now that works great if all the jobs are the same size. In reality, they're not. Some jobs are just bigger than others. And so what we do is we actually assign a value to each job. Again, we call it a number of slots. And we have a theoretical maximum number of slots that we can effectively handle at a time on the machine. And so we go to the top, we say, okay, 1 slot job for our first customer, that's great, put that in 1 slot. Next job requires 3 slots, let's fill in those 3 slots. And we kind of go through it. Okay, 2 for you. And then we say, oh, we don't have enough slots available. Okay, we need 4 slots for this job. So we're going to wait until some slots free up. We're not going to move on. We're just going to wait till some slots free up and then fill them in with this job. Go back to the top again, same thing, wait for some slots to free up. And now we hit an interesting situation. So this yellow customer, the envelope customer, already has 2 slots they're taking up. They're asking for 3 more. We actually limit. Generally, a customer can only have up to 50% of the available slots total associated with them. And so 2 + 3 is 5. 5 is more than half of 8. And so we're actually just going to move on. We're going to say, well, when you finish up with the previous job, we can then process the next one in line. So we go to the customer on top, and they right there for them, it's 2 + 1 is fine. We're just going to wait till some space frees up, fill in that slot, go to the next one, and oh. No, we're not going to stop there because, again, they didn't finish. But actually, the customer on top also now is asking for 2 slots. They already have 3, so they're also asking for too many. So we end up basically bouncing back and forth until such time as one of the customers finishes their jobs, and then we can fill in some more slots. Now, it might be a little bit confusing as to why we're insisting you can't fill too many slots for one customer. But we'll see why this actually makes a lot of sense. So we're going to go to the top again. Some slots get freed up, fill in with the 2 job. And now let's say, the customer at the bottom, the blue customer, has another job that requires 4 slots. So we're actually going to wait for them. We're going to wait until some more capacity gets freed up, and then they're going to get first dibs on the slots. So it creates a situation where we are reserving some capacity for other customers at all times, even though we're not fully using all our cores all the time, but it makes a fairer experience for all the other customers, making sure there's always some capacity to take in their traffic. And then we can go ahead in terms of the rules we established earlier. Okay, this idea of the fair queue lives between the I/O and the CPU layer, and it is implemented in Go. So some more Go in our system. There's one more element to this whole thing, which is that we prefer synchronous to asynchronous requests. If there's anything that's going on in the background, we can just retry it later. It doesn't really need to be done right now. So if we happen to be having a spike, and usually again everything makes it through the queue like basically immediately, right? We reserve enough capacity for that. But in a situation where there is a big spike, then the fair queue comes into place, and then we say, okay, async request, you got to back off for now while we scale up. Okay. We also have, by the way, a similar system for database access. So we have, again, a queue of queues, not with like the number of slots. It's not anything as complicated as that, but we do have a queue of queues to make sure that each cloud can't access the database too much at the same time. How it's implemented is one gigantic monkey patch to active record, mainly to connection pool. So we're actually divvying up the connections amongst the clouds in this more fair way. Okay, it actually touches a lot more classes than that, but this is kind of the main one. And background jobs. So the principle is that anything that can be done out of band should be done out of band. So for example, Cdn invalidations definitely should be done in a background job. No reason to do that as part of let's say an API request. We have webhooks that can happen as a result of uploads or other operations. Those also happen in the background, and we have eager transformations, right? This is kind of the big use case in terms of the delivery flow, right? The processing part of it doesn't actually have to happen when you first expose your site to users or your image to users. It can also happen in advance. You can just tell us, I'm going to need this, and then we generate it, and then it's just there. Faster experience for your users, and it definitely helps our own systems bear the load. So human factors. This is the last bit, and there's this just hilarious quote from Ted Nelson. The good news about computers is that they do what you tell them to do. The bad news is that they do what you tell them to do. And the idea is that we can scale by humans if we help humans tell the computer more scalable things to do. So the first prong of our basically two-pronged approach is education. So we will encourage practices like eager generation, which are good for our systems, but also good for the customer. And then there's the element of relationships, cultivating the kind of relationships with our customers, understanding their use cases and how they might use our system and what kind of stresses they might place on the system. We create a situation where if they're going to make a big change in use patterns and they want us to be ready, they just let us know about it, and we're happy to scale up in advance and make sure that we're ready for that kind of spike. It's ultimately this is all about win-wins, looking for the ways that we can help the customer while the customer helps us, and everyone really has a better outcome from that. If we have a really big customer, they're going to have a big spike. Like if they tell us, everybody wins, right? All of our customers get a better experience. That customer has the capacity ready for when they need to do their change, and we're able to not have PagerDuty wake us up in the middle of the night. Let's finish up by talking about Cloudinary on Rails. But I want to point out that this talk was not really a Rails talk that much. Most of our traffic never touches Rails, really only about 1%. The fastest parts of the system are not written in Ruby, right? They're written in Go or Scala. The computation-heavy parts are low-level utilities or APIs. In certain cases where we have more like AI-focused groups in the company have certain APIs that we also use for transformations. The database scaling is language independent. We did have to make some changes to Active Record, but the strategy itself is not really dependent on a language. So all this to say that the challenges of scale are challenges of scale. They're not Rails problems per se. Actually, Rails is really great. It's been a great way to build this system. For the first about 4 years of the company, the company was founded almost a decade ago. For about the first 4 years, it was mainly worked on by 2 developers, and they developed already the core features of the system during that time. And it's been working for us since then. Ruby is really great for creating interfaces, whether it's interfaces with APIs, interfaces with shell commands, low-level utils, whatever it is. It's a really good language for that. We did need to move a few things out of Ruby, but this is not like one of these stories where, oh, we just rewrote our whole app in Go to solve the problem. No, we moved the most performance sensitive parts. Anywhere where there's a big win to be had by moving out of Ruby, we did. That wasn't a problem. We didn't stick with Ruby just to be dogmatic about it. But we also, we didn't find out there was really a need to leave Ruby or a need to leave Rails. It's been a great system for working with. However, there have been certain challenges. So primarily upgrading Rails is always hard. There's a reason that every single conference has a couple of talks about upgrading Rails and the challenges and how they overcame them. If you've monkey patched deep into the internals of Rails and especially Active Record, it gets even harder. And there are some issues specific to Israel. The primary Cloudinary R&D center is in Israel, and it is actually pretty difficult to recruit Ruby developers here. There are not a lot of ways that Ruby developers get trained. Usually it's people who are trained in other languages. They migrate over, but you don't have the abundance that you have in a world of boot camps and things like that. And developers in Israel don't always want to learn Ruby. It's not necessarily a language that they think is going to get them their next job, and so they might not want to take a job in Ruby at all. So the future of Rails at Cloudinary is a bit of a mixed bag. It's here to stay. We have tons and tons invested in Ruby and in Rails, and we still do enjoy, I think, working with working with Rails. But we are moving in the direction of breaking off bits of the big Rails monolith into polyglot microservices. And the goal with these microservices is not that they're going to be written in the best tool for the job, so to speak. But really, it's more of a human thing. It's about building the app that our next employee wants to work on. And if Rails can't be that, then unfortunately it's not going to be that. However much we love Rails. So that's a little bit of a bittersweet ending, and I apologize for that. At the same time, again, this is not relevant to you if you are in a part of the world where Ruby and Rails are still pretty popular, which I get the sense that they are in many parts of the world. And if you're on a globally distributed remote team, which are becoming more and more of a thing these days, then you're fine. There's plenty of developers who want to work with Rails. It's not actually going to be a challenge for you. And the main story in that case is that Rails has been a really productive environment in which to work. We didn't have to get that much out of Rails. We didn't have to write our whole app in something more performant or anything like that. It wasn't necessary. And Rails really is a potentially a great trail to scale without fail. That's what I have for you. Thank you so much to everyone who was part of this process, helping me with the talk. Thank you to you, all of you, for listening. And you can see, aside from the Q&A, of course, you can see right on top where to get access to me if you have questions. Thanks so much, and have a great rest of the conference. Bye.